If you feel confident in your ability to find the domain of a rational function, then you are well along your way to finding the equation of a vertical asymptote. Those two concepts are closely related. In section 4.4.3, we'll learn how to find both vertical and horizontal asymptotes. Remember, those are the only two forms of asymptotes that we're focusing on in this course. Other forms, oblique asymptotes, also known as slant asymptotes, do occur in rational functions, but we're going to focus on the two most fundamental, which are vertical and horizontal. These are used as guidelines in graphing functions. We are going to approach these one at a time. So let's first focus on vertical asymptotes. The equation for a vertical line is always x equal to a constant. So when we express the location of a vertical asymptote, we must do so in equation form. These will occur when the denominator is equal to 0. Remember, when we found the domain of a rational function, we set the denominator equal to 0, and we called those restricted values. Well, vertical asymptotes occur at the restricted values of the domain. Rational functions may have 0, 1, or many vertical asymptotes. Graphs never intersect a vertical asymptote. So the main key here to finding a vertical asymptote is to note that they occur where the denominator is 0. Now, we're going to skip horizontal asymptotes for now. We're going to go to example 2, and we're going to find the vertical asymptotes for all of the examples. Then we'll come back and we'll do horizontal asymptotes. This way we can really focus on one skill at a time. Example 2, for the following rational functions, write the equation of each vertical asymptote, and then write the equation of each horizontal asymptote. We'll catch that on the next round. If an asymptote does not exist, so state. Example A, we have y equals x cubed divided by x plus 1 times x minus 4. Remembering that a vertical asymptote occurs where the denominator is equal to 0, we need to find the zeros of the denominator. In this case, the zeros of the denominator are x equals -1 and x equals 4. And notice I just wrote the equations of those vertical asymptotes. These would be the restricted values of the domain. So, by the way, the domain of this function would be from -infinity to -1, union -1 to 4, union 4 to infinity. So at the restricted values where our domain changes, that's where we're putting the boundary line called the vertical asymptote. The same thing is true here. We have excluded 4 from the domain because at 4 there is a boundary line known as a vertical asymptote in the graph. So again, these two skills are closely related. Looking at the next example, the denominator on this one is not factored, so in order to find the zeros of the denominator, we'll have to put in a little bit of work and factor this function. It's not a big deal. Notice in the first two spots, we're going to need an x and an x. The product of the last two terms need to be 10, so by trial and error, eventually we would end up with this factorization. Then we're able to observe the zeros of the denominator. If I set that first factor equal to 0 and I solve for x, I end up with x equals 5/2, and very easily we can read the 0 out of that second factor to be x equals -2. So this function has, again, two vertical asymptotes. Now let's go ahead and practice the domain. Notice whenever we find the domain, it's really important that we get these numbers in order from left to right. So I'm going to use the number line kind of as a guide here, and I'm going to identify the 3 intervals as divided up by those restricted values. So the domain would be from -infinity to -2, -2 to 5/2, and 5/2 to infinity. So again, at the restricted values of the domain, which we are excluding by the use of our parentheses, that is where the vertical boundary line exists in the graph. So again, at the restricted value from the domain, that is where the boundary line occurs in the graph. This graph has two vertical asymptotes. Notice there are three parts to the domain. So this graph would actually have three branches divided up by those two vertical asymptotes. Let's try that one more time on example C. We're starting with the vertical asymptotes. Remember, vertical asymptotes occur at zeros of the denominator. In this case, we're going to need to solve a quadratic equation. We can do that by factoring. And remember, if you're not a fan of factoring, you can always use the quadratic formula, or you can even now use the synthetic division process to find your factors. That's an option as well. So this one would factor as x minus 7 times x plus 3. So we're going to get 2 zeros from the denominator, and when we write it like this, we have actually expressed the equation of those vertical lines. For practice, let's find the domain. Remember, the domain is everywhere except where those vertical asymptotes occur. So this would be from negative infinity to negative 3, from negative 3 to 7, union 7 to infinity. So again, the domain excludes the restricted values by using the parentheses, but at those restricted values, that's where we find those vertical asymptotes. So finding the domain of a rational function is very closely related to identifying the location of those vertical asymptotes. So that takes care of our first type of asymptote, vertical asymptotes. Let's go back and learn how to find the equation of a horizontal asymptote. First of all, the equation for a horizontal line is in the form y equals a constant. When we express the location of a horizontal asymptote, we must do so using the correct form for the entire line. For example, I don't want to say a horizontal asymptote occurs at 2. I would say the equation for the horizontal asymptote is y equals 2. Rational functions can have at most one horizontal asymptote. So there is either 1 or 0. It cannot have more than one. Now, the graph can cross a horizontal asymptote on its interior. A horizontal asymptote really describes the end behavior of the graph. What happens on the extreme right and left-hand sides of a rational function? Does it settle down below some sort of horizontal asymptote, or does it increase without bounds to infinity? So horizontal asymptotes are a little different from verticals in the fact that your function may cross a horizontal asymptote on its interior. So don't be alarmed if you see that happen. It does happen sometimes. Now, the way we find horizontal asymptotes is completely different from the way that we found our vertical asymptotes. Remember, to find a vertical asymptote, we're looking at where the denominator is equal to 0. To find a horizontal asymptote, we're going to use the 3 rules related to the degrees of the numerator and the denominator. So, at first, these rules can look intimidating, but once you learn them, really there's no work to show. You'll be able to look at the function and determine by looking what's the equation of its asymptote. So we determine the location of a horizontal asymptote by examining the degrees of the numerator and the denominator. So we have 3 possible relationships between the degrees of the numerator and the denominator. Case 1, the degree of the numerator is less than the degree of the denominator. So I'm going to write this: the degree of the numerator is less than the degree of the denominator. In that case, there is a horizontal asymptote. There is a horizontal asymptote. I'm just going to abbreviate it HA at y equals 0. That would be the equation of the x-axis. So if the degree of the top is less than the bottom, automatically the equation of the horizontal asymptote is y equals 0. Second case, the degree of the numerator is equal to the degree of the denominator. So if the top and the bottom have equal degrees, then there is a horizontal asymptote at y equals the ratio of leading coefficients. Sounds like a more complicated rule, but when we do an example, that will be very easy to understand. So if the degree of the top is equal to the degree of the bottom, then I'm going to find the numerator's leading coefficient and the denominator's leading coefficient and form their ratio. Whatever constant I obtain there, the equation of the horizontal asymptote would be y equals that constant. The third case, the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. Now there's a fun little way to remember at least two of these rules. It's called Bobo-Botten. Maybe you've heard that before. Bobo-Botten. Bobo stands for bigger on bottom 0. Bigger on bottom 0. So if the degree of the denominator is bigger, that is, it's bigger on the bottom, then the equation of the horizontal asymptote is y equals 0. So Bobo, bigger on bottom 0. Botten stands for bigger on top none. So if the degree of the numerator is bigger on top, then there is no horizontal asymptote. We don't have a catchy little phrase for case 2, numerator equal to denominator, where we get the ratio of leading coefficients. If you come up with something, send me an email. I would love to hear it. So let's apply these 3 rules to the same examples we were looking at previously. So now we're working on part B. We want to write the equation of each horizontal asymptote. Remember, to find the vertical asymptotes, we look at the denominator. We find the horizontal asymptotes completely different. So we need to identify the degree of the top and the bottom. So the top of this particular example is degree 3, and the degree of the bottom, if I were to FOIL it out, I would see an x squared term, so it would be degree 2. So in this case, it's bigger on top. So I'm thinking of the Botten case, right? The degree of the top is greater than the degree of the denominator. Therefore, there is no horizontal asymptote in this case. On our next example, focusing on horizontal asymptotes, we need to identify the degree of the top and the bottom. The top is degree 2. The bottom is also degree 2. Remember, degree is the highest exponent I can find on the x. Therefore, we are looking at this special case 2. The degree of the top and the bottom are equal. Therefore, the equation of our horizontal asymptote is y equals the ratio of leading coefficients. So the horizontal asymptote always has the form y equal to a number. Now I'm going to form the ratio of leading coefficients. So the coefficient on the top, leading coefficient there is 1. Leading coefficient on the bottom is 2. So the equation of our horizontal asymptote is y equals 1/2. Let's go ahead and verify this visually by looking at the graph of this function. So I'm going to type in the original function, being careful to put both the numerator and the denominator in a set of parentheses. Now, if your calculator has that 2D format and you can actually see the individual levels of the fraction, you won't have to worry about those parentheses. Now, don't forget on this one, we found 2 vertical asymptotes. We found a vertical asymptote at 5/2, which is 2.5, and also -2. So our calculator has a little bit of trouble sometimes graphing near an asymptote, but do notice there are 3 branches. Those 3 branches are separated by 2 vertical asymptotes, and we can take it a step further and actually type in the equation of our horizontal asymptote, which was y equals 1/2, and notice the long-term behavior on both the left and the right. limits the curvature of that graph. That is, the graph follows that asymptote on its way out to the left and to the right. Now, to make this just a little bit easier to see, I'm going to change my y minimum and y maximum from -2 to 2. I'm just sort of shortening the vertical view of this graph, so maybe you'll understand the behavior of the graph a little bit better. Again, you can see those 3 branches. The domain would have 3 separate intervals. They are divided at x equals -2 and x equals 2.5. That's where our vertical asymptotes are located. And you can also see how to the right, the graph levels out under our horizontal asymptote, and to the left, the graph levels out over the horizontal asymptote. Hopefully it's making sense and all coming together. Let's do this one last example here. We're looking for the equation of a horizontal asymptote. Remember, to do that, we identified the degrees. The degree of the top is 1, and the degree of the top is 2. So the degree of the numerator is less than the degree of the denominator. So this case is Bobo, right? Bigger on bottom. Bigger on bottom, 0. Therefore, the equation of our horizontal asymptote is y equals 0. So if we examined the graph, and you can do that if you want to, we would see the graph leveling out near the x-axis on the left and right sides. So, bottom line, to find the equation of a vertical asymptote, determine the zeros of the denominator, and remember the equation of a vertical asymptote is x equal to a constant. Then, to find the equation of a horizontal asymptote, we compare the relative degrees of the numerator and denominator, and we apply our 3 rules. You can remember it as Bobo-Botten plus that special case where you've got equal degrees like in example B. The form for the equation of a horizontal line or a horizontal asymptote is y equal to a constant. And remember, all of this can be verified with your calculator, but be very careful when you plug in a rational function. Make sure you get both the numerator and the denominator separated in a set of parentheses.